surfaces. Right. Yes. So thank you. Right. So uh, should I work here? Okay. So yesterday, Professor Balaji introduced you all to the how you define curvature of a plane curves, right? So you have a curve in the plane. You define. I mean, you take a point here. You find the best fit circle. So okay, which he explained as you take a tangent here, and clearly, I mean, the limit as the circle gets larger and larger is this tangent line, and the limit as the circle gets smaller and smaller is this point. In some sense, the circle initially is on this side of the curve, like this side of the curve, and then eventually it's between the curve and the tangent line. And so somewhere in between, it's kind of hugging the curve in the best possible way. And essentially, then the heuristic is that, I mean, or not a heuristic, this is the definition. So the motivation is that we think of larger circles as being less curved and smaller circles as being more curved because for example, you could take the extreme case, right? You take a circle whose radius goes to infinity, you get a straight line. We all agree that straight line should be flat, correct? Right. So so I'll just mention this now. We also can think of it as, so we take 1 over the radius in some sense because, so if you have a small circle of radius, say little r, and you have a larger circle of radius r, so we're kind of measuring rate of bending, right? So if we want to talk, so to kind of subtend the same angle, right, on both circles, on this circle you have to traverse a much larger distance, right, than this one. And the distance, and in fact it's given by simple scaling, so you have to travel r times more distance on this. So it's essentially, you take your unit circle as you calibrate that's your calibrating circle. You set that to curvature 1, and then any other circle you just say it's 1 over so for any arc, you take the corresponding arc, and then however much extra distance you have to cover, the scaling, you take it as 1 over that. So it's kind of given some angle subtended, it's kind of measuring how much distance you need to cover, how much more distance you need to cover, like the scaling, right? This kind of is a useful way to think about it later on. So, and when he was showing that the center of curvature does in fact exist, he considered, say, like he considered tangents to adjacent points, and he considered the normal to this and the normal to those, and he kind of tracked where this intersection went as this point approached this point. So in some sense, so you're kind of taking these two tangents are given by the derivatives of the curve, and kind of when you take the difference and you track this point, you're essentially keeping track of second derivative information. You're kind of taking derivatives of two different points and you're doing some kind of limiting process where they come together. So in some sense, you're kind of tracking how the derivative is changing. So another way you might think to define curvature is, if you were to take, so you take your, so you only care about directions, right? So you take the unit tangent to every point on the curve. So if the curve is given by gamma being so curves are just functions from an interval for plane curves to the plane, right? So you can take and we assume that the derivative is non-zero everywhere. So you can just take the derivative of gamma. So if it's, say, gamma of t, then you say d gamma by dt, which is like the tangent, the velocity of this curve at every point. You just normalize it to 1. So we'll call that t hat, the unit tangent at every point. We'll say t hat at p, right? So say this point is p. And we want to say how this tangent is changing as we move along the curve, which is kind of also, you're kind of seeing how the direction changes as you move along the curve. So it's kind of, you seem to kind of be trying to track the same thing. So you could do, so this tangent at a point is a function of t, right? Because the point is a function of t, and the tangent is determined by the point. So you could do dp by dt, but then it matters what kind of parameterization you're picking for the curve. So for example, I could go traverse along this line at double speed, Okay, so maybe this is a bad example. I could move along this arc at double speed, right? So the tangent may change twice as quickly, but I mean the arc is the same. Like the geometry of the image of the curve is still the same. So we don't want that to come in. So what we'll instead do, we'll say dp by ds, where s is the arc length. So you take the tangent at this point. So maybe I should remove all this. So you take the tangent at this point. You take a tangent at some small distance ds away. Sorry, that's not okay. Let's say small distance h away along the curve, and you can just like your regular limit. So you do t of p. Say that point distance h away is p prime. You just say t hat p prime minus t hat p by h, limit h goes to 0. Right? So same way you define derivatives. And this is, so you can just take the, like, you just care about the magnitude. I'm claiming the magnitude of this is our curvature. And in fact, I'm claiming that it agrees with the notion of curvature we have already. So why am I saying this? So, excuse me. By the way, in effect, how we end up computing this is you take dp by dt and you take the rate of change of arc length with respect to time, right? So, I mean, this is just like a chain rule of sorts, right? So, I'm claiming this ds. So you can just bring this here, do chain rule, and you'll get this, right? By the way, I can assume derivatives and chain rule and things like that. Is everyone okay with that? Anyone uncomfortable? All right, cool. Right. So, yeah, in effect, we compute it this way, and we just take the magnitude to say curvature. Now, why am I claiming this? So I'm essentially saying that. So we can just do this explicitly for a circle. The calculation takes 2 seconds. So you have a circle, right? R, and you parameterize it with r cosine of t, r sine of t ranging from 0 to 2 pi, right? And then so the tangent at every point. So say t. The tangent at every point, I mean, you can either differentiate this or you can just see that it's perpendicular to the radius. So it'll be minus r sine t r cosine of t. And then we normalize the tangent, right? I'm saying we take the unit tangent. So we remove these r's. So this is our t hat, which is implicitly a function of t, right? And so dt hat by dt is just minus sine t minus cosine of t minus sine of t. All right, and so this is the numerator. Denominator is essentially, so ds by dt. We kind of define arc length heuristically as, say, you take a little change in x and the little change in y, and you do Pythagoras on them, and you call it dx squared plus dy squared. This is the heuristic, and based on this heuristic, we define ds by dt. So if we were to divide this by dt, this will just be dx by dt square plus dy by dt square, right? And so this is like the rate of change of arc length. So I mean, this leads to our usual arc length formula. Some of you might be familiar with. So it'll just be arc length is just the magnitude of d gamma by dt, say going from a to b. That'll be the arc length of this, right? So you just differentiate this expression and you just get, so this is s, right? So you just differentiate this expression and you just get this as ds by dt, right? So that's fine. So in our case, so we have gamma. D gamma by dt is, well, t hat without the normalization, right? And it should be the magnitudes of these. You can't divide vectors like this. I mean, that's why you need to take magnitudes, right? You take magnitudes of both of these, and I mean, you don't need to take a magnitude here. This is just a scalar. But yeah, right? So the magnitude of this is just 1. And then the denominator is just ds by dt. So that is the magnitude of this. So it's the magnitude of, well, it was our d gamma by dt was minus r sine t, r cos t. So the magnitude of this is just r, right? So you recover for a circle. You find that this formula agrees with the radius of curvature definition for curvature, right? So, and kind of, now this is a bit disingenuous, but I'm kind of defining the best fit circle as the circle such that uh, it's tangent to the point. It shares the tangent at this point, and it kind of excuse me. It has the same curvature, right? So I mean, like if you were to actually define it formally, you kind of have to define it this way. So it's kind of circular, but if you take this as your definition, you at least get that you recover this for circles. So it makes sense, right, that we do all this. So this is what we do for plane curves, and yeah, I mean this is nice. This gives you some nice things. So for example, if you were to take the curvature at every point, so I believe the notation we used was kappa of p, right? And if you take kappa of p and you integrate it over gamma, so essentially, so this will be kappa of p of t, right? Or kappa of gamma of t, integrated from a to b dt, right? This is the total integral of the curvature around the loop. So total integral of the curvature, and this is in some sense, okay. So say gamma is a closed loop. Sorry, I should specify that, such that it never intersects itself. Then we can kind of, like, you get the result that this is just 2 pi. So that, like, the total turning when you go around a closed loop, as long as when you go around a closed loop should just be 2 pi, right? And so essentially, the reason you can't go around twice is that then the loop would have to intersect itself. This is a topological fact, really. This is kind of non-trivial to prove, but I mean, if you accept the fact that given some angle theta, there's a unique point on the loop at that angle, so with respect to some reference line, then this comes out, because this essentially is related to d theta by dt. So you get this nice result, and so yeah, this is plane curvature. Now, another nice way to motivate this is, so this is a physics explanation in some sense. So those of you fresh off of high school physics might recall. So there is, right? Okay. So I said, right. So the curvature is kind of tracking second derivative information, and so in some sense it's kind of tracking the acceleration of gamma, right? And you get this very nice, like, uniform result for a circle where every point is 1 over r. So when you do, so in high school physics, like, does anyone remember anything to do with trajectories along a circle and acceleration? There's a very standard formula that you guys use, right? Like, can anyone just v square by r? Exactly, precisely. So you have 8, so I'll call it A tangential, so parallel tangential, okay, equals v square over r, right? So so you can really, if you want to compute the curvature of any curve, well, the tangential component of its acceleration you can compute, right? You just take the second derivative of gamma, right? And then you know the derivative of gamma. You take the component along that, so d square gamma by dt square, and then so taking the component, so you can do this, you can take the dot product, and so d gamma by dt, and this is like the standard way to project one vector onto another, right? So d gamma by dt square times e gamma by dt, right? This is just, you take the component along it, and then this is just a normalization, right? So you can compute this, because we're assuming you know the parameterization explicitly, right? You can compute this. You can compute v square, that just d gamma by dt square. So you can compute 1 over r as just A tangential by v square. So this is kind of like a kind of physics argument to. So the reason you can do this is, so I'm essentially defining a best fit circle in some sense, the definition we've given is a circle such that the velocity is in the same direction. Okay, right? That's what it means to share a tangent. And the acceleration. So say okay. There's this fact about curves where you can always parameterize them to have a constant unit speed throughout. Okay, you can always just reparameterize. So you can take some rescaling of your interval, appropriate rescaling, given by the speed at each point on this interval, such that this absolute value is just one always, right? So you're kind of parameterizing it. So you take some starting point gamma away, and you're kind of parameterizing the curve by the arc length along the curve, right? So we're saying gamma of s equals the point at a distance s away from gamma away. Or sorry, gamma of s plus a is the point at a distance s away from gamma away, right? So really then you can just ignore this, and so, but yeah, I mean you can ignore this even, and then you can just calculate the acceleration in that unit speed parameterization. But essentially we're saying that by defining our definition of the closest fit circle is a circle in which when you pick a unit speed parameterization, this tangential acceleration is the same. So you can kind of just say, okay, whatever my tangential acceleration is the same as the tangential acceleration on my unit speed circle, and then on that circle this formula holds, right? So this is just a neat way to just an argument to say what the curvature should be at a point, right? And so yeah, I mean this is kind of like this is one physics explanation that I could think of, as was promised. So this is very nice, but you can't. I mean of course there are many things to do, but with plane curves, but it's kind of plane curves are kind of simple in the sense of like that unit speed parameterization I mentioned. You can parameterize the arc length, so that in some sense, if you have some curve that's not closed, in some sense, all those curves are basically just the same as an interval. Like you can take a mapping from an interval to these curves such that all the distances are preserved, and and topologically speaking, yesterday, so then I mentioned homeomorphism. These are homeomorphic as well. So like these are kind of simple things, plane curves. So we want to, but curvature, this notion of curvature that we've introduced, is very powerful. But unfortunately here, these are too simple for us to really need it to do anything. So, but if we can kind of extend this to higher dimensions, so surfaces, say for example, surfaces in 3 dimensions, we can introduce a notion of curvature for them, then maybe we can have some interesting results, because surfaces are very non-trivial. Like surfaces are much more complicated than curves. I mean, not every surface is just like some, the term is isometric, in which like there's a distance preserving map to some region of of the plane, of the real plane, like R2, two-dimensional Euclidean space. So fine. So first say we have some surface. Right? And you have, now we don't know how to define curvature on the surface just yet, but you can kind of say you have some curve on the surface, call it gamma again. So yeah. In this case, so the thing is, now you have to worry about 2 different directions. So in some sense, I suppose you could think of it as a best fit ellipsoid instead, where you kind of take curvature in one direction, curvature in another direction, and that kind of gives you like, but those might not agree, so you kind of have to do it with, something like that. So, yeah, so some of you might know where this is going. So I want to talk about, say, the curvature of forget a curve. So on a surface, I can at least, so if you think about it, you can at least talk about curvature in a given direction already. So what does that mean? So you take, so every surface, there's I should actually define, I think it's okay. A surface is like something where in some region, you can parameterize it with 2 variables, right? So you can take some map phi from, say, some rectangle. So like this coordinate rectangle, right? So 0, without Lasso generality, so 0, 1, like a square to some region, right? Some rectangle to your surface, such that, so essentially you can describe points on these uniquely by points on these via phi. So phi of AB defines a unique point on here, and in particular, and this map is kind of differentiable in the sense of if you so phi of you have phi of xy, and if you keep the y coordinate fixed, this is a single variable function, so that partial derivative should exist, should be continuous, and same thing for the partial derivative with respect to y, and in particular this thing called the gradient, so the vector formed by with the components of these two partial derivatives, this should be non-zero at every point. Okay. This is just because, for example, otherwise you could, for example, just collapse this whole thing to a point, and that's not very surface-like, or like there could be some kind of pinching that happens at a point or something. You want kind of like a smoothness to your surface. So this being non-zero gives you that. Anyways, so in particular, and also this, no, actually this is fine. That's fine. Oh no, I said this wrong. Like both of these should be non-zero. Both of these are vectors in their own right. Each of these should be non-zero. Anyways, and they shouldn't be, they kind of shouldn't line up together. So essentially, what these are doing is, so partial phi partial x is kind of taking these lines and kind of giving you the corresponding lines here, and you can take these grid lines and you get other corresponding lines here, and essentially you want grid lines to not line up with each other, otherwise it kind of breaks your coordinate system, right? You want a unique grid line, you want a unique vertical grid line and a horizontal grid line through each thing. That's what a parameterization means, right? So just a small digression. Anyways, but so now say you have, so now we don't know what it means to talk about the curvature of the surface at a point, but we can talk about the curvature in a given direction. So you can take your surface, right, and you can intersect it with some kind of plane, right? So say the intersection of this plane is like this, right? And so this kind of defines a unique direction on your surface. So a plane passing through, say you start with a given point, you take a plane passing through it. This kind of defines a direction on your surface, right? And the intersection of the plane with the surface defines a curve on your surface, right? And this curve lies in a plane, so we're back in familiar territory. We have plane curves, right? So we can now do the exact same thing here with talking about the curvature of plane curves and things like that. But we want to kind of yeah. So in fact, so given a direction, you can kind of call this the curvature of the surface in that direction. Like you just take like a plane section in that direction, and you get the curvature of the surface, right? It's just the curvature of the intersection curve. And explicitly, so you have like a unit normal at every point. So these two are kind of tangent vectors on your surface. So kind of this maps like this. You can think of this as like you take a small vector here, and it gets mapped with this scaling to d phi by dx on your surface here. Sorry, partial y partial x here, and partial phi partial y here. Like this basis here gets mapped to like a basis here of vectors, right? And this kind of these two kind of span a tangent plane to your surface here. So in particular, this tangent plane has a normal to it, right? And we'll just normalize it to make it a unit normal. And so this is kind of the same. It's like a similar thing to the unit tangent here. So the thing is, we could have, instead of tracking the unit tangent, we could have tracked the unit normal here, because given a unit tangent, there's a unique unit normal that is, say, counterclockwise 90 degrees to it, right? Like you have this unit tangent here, you just rotate it by 90 degrees to get a unit normal to your curve, right? And you're kind of tracking how the direction of the tangent vector changes. This unit tangent vector changes. It's the same thing as tracking how the direction of the unit normal vector changes. Like both of these are related by just some fixed constant angle. So this is essentially the same thing. So here, if you were to consider the rate of change, so if you were to do a similar parameterization, like a unit speed parameterization, and you kind of take the rate of change of the normal. So I'll use the notation. So if your direction is, if it's in the direction of a vector v, which we'll say is also a unit vector, because we only care about the direction really, we can say that like this is tracking similar information, but it's not quite the same, because so if you have, say I have, this is my planar section and this is my surface along it, right? My surface, like the normal to my surface, say my surface is like this. If my surface turns like this, my normal is kind of turning with it as I move along the plane. But I only care about my surface kind of turning. I only care about how my normal changes in the plane. Kind of like how the surface, like, because the curve itself will not change, right? If I take this intersection, or if I take an intersection like this, the curve itself does not change. So I don't care about the angle in this direction, in the normal direction to the plane whose intersection I'm taking. So I only care about the direction, the thing in the direction of v. So I'll just take the dot product with v, and you can check that this gives you the same answer as this. These two are the same thing. Okay, so you can calculate it both ways. So this is nice. So now given a direction, you have a curvature associated with that direction, right? And in fact, yeah. So now, if you want to say associate a single number with the surface as a whole, one thing that you could do, so there's a few ways to do this, but one way you could do it is so given a point, you consider all the imagine you're looking the surface from the top. So given a point P, there's a bunch of unit vectors emanating attached to P, right? And you can look at all these directions, and you can look at the curvatures in all these directions. Now, so essentially, you're kind of thinking about curvature as a function of some kind of unit circle, function of the unit circle, because like a unit vector is a point on the unit circle, right? That's how you define it. So essentially, as a function of this, as a function of the circle around your point, you have the curvature, and so at some point you attain a maximum curvature, and at some point you attain a minimum curvature. So I mean, does everyone know the fact that if you have a continuous function from a closed interval to the reals, it has like a maximum and a minimum? It's the same reason for the circle, same kind of reasoning. So it attains a maximum and a minimum, and the really neat thing about it is these maximum and minimum are always attained in orthogonal directions. So if the maximum is attained in this direction, the minimum will be attained in the direction orthogonal to it. So if you want a justification, just small digression into some linear algebra. So this map that you're considering, this unit normal times so this is some function of v, right? So I'll call it, the standard notation, we call it LP of v. This is some function of v, and essentially this is a linear map over vectors tangent to this point, to the surface, and these are essentially the eigenvalues of that linear map, and this map is like the map is is given by a symmetric matrix. So anyone who knows the spectral theorem knows that the eigenvalues are orthogonal to each other. This is, if you don't know what that means, that's okay. It doesn't matter. But the neat thing is that these always end up being orthogonal to each other, and you kind of define the curvature at the point as the product of the curvatures in these two directions. Okay, so this is our definition of curvature, but I mean, it might not be completely obvious why we define it this way. So I call back to this thing that I talked about. It's kind of so here we're saying the angle subtended. It's like you have to cover that much more distance. Like you have to cover, you have to cover 1 over the curvature more distance to subtend the same angle, right? So we can do a similar thing here, where so essentially this unit normal that I'm talking about, right? So this kind of defines the like the direction your surface is facing at every point. So and this unit normal, so essentially you like all these directions you can think of as lying on the circle, on the unit circle, right? Like so, like n you can think of as sitting as a vector sitting at the origin. You can just bring it to the origin, and like the tip will lie on the unit circle. This is kind of giving you the direction of your surface. So as you move p around, this normal will kind of move around the circle, the sphere, right? And essentially, so this is giving you like a map from the surface to the sphere, and kind of the area that you cover here, like so. And in some sense, so when we talk about curvature, we're talking about the derivative of this map. So if you were to so if you the derivative of this map is given, so these two principal curvature directions are essentially when you vary the curvature in this direction, the normal vector kind of also moves purely in that direction. That's kind of why they end up being principal curvatures. So, and the same goes for the other direction. So in some sense, if you take like a small circle here, it'll be scaled by the principal. So the curvature is just the derivative of the normal, right? So if you take like a small variation in one principal direction, if you move your point slightly, the normal will also kind of move in some direction proportional to the curvature in that direction. And likewise for the other direction, it'll kind of move a little bit proportional to the curvature in that direction. So kind of so this entire area kind of gets scaled by the principal curvatures in two orthogonal directions when you move here. So in some sense, you're kind of measuring. It's kind of like you know that on a circle, area is directly proportional to like the solid angle, right? That's how we define it. We define solid angle as of a region on the sphere by area over the radius, right? Radius squared, or something proportional to that. I'm not sure what the normalization is. So it's you're kind of measuring how when if I were to pretend that so the nice thing about a circle is when you vary a point on the circle, the corresponding unit normal, sphere, the corresponding unit normal kind of varies with that point, right? It's just in the same direction as the position vector all the time. So you're kind of saying, pretend I'm actually on a sphere, right? And kind of, we're kind of measuring how much, for a given area, we're kind of measuring how much solid angle I'm subtending on that sphere, right? So this is again kind of measuring how much you're bending, because again, so if you work this thing out for an arbitrary sphere of radius r, you'll get that this product of the principal curvatures comes out to 1 over r squared. Why? Because you can just consider a sphere, right? Consider any point on the sphere. Now all directions are symmetric on the sphere, right? So every direction is a principal curvature direction. So you consider this direction on the sphere, you consider this direction on the sphere, two perpendicular directions. We know what their individual, like these two curves, we know. So the intersection of a plane with the sphere, we'll take the plane to be passing through the origin, is just a great circle of the sphere. And we know what the curvature of a plane circle is, right? It's just 1 over r. So both of these circles have curvature 1 over r. So this becomes curvature 1 over r squared. Their product is just 1 over r squared. So in some sense, and this kind of extends the same analogy that we had here, because you're essentially saying that on a sphere of radius r, if I take the sphere of radius 1, if I take these are similar figures. If I take the ratio of the area of corresponding figures on both of these circles, this one will have 1 over r square of the solid angle. Sorry, the area will be r squared times the area over here. So the curvature is just inversely proportional to that. So it's extension of the analog. I know a little bit is lost here. This is a bit mysterious. For those who want this, you can just take the derivative of this normal map. So the matrix of partial derivatives, and take as determinant. That's all we're calculating here, because that's what the product of eigenvalues is, right? It's just the the determinant of the map is the product of eigenvalues if it's diagonalizable, right? Anyone who knows what that means, that's how you'd actually compute these things. Everyone else, it's okay. It doesn't matter. This is kind of the heuristic for it. Now, yeah. So and here I've kind of also touched on the fact that curvature has to do with area in some sense, in that if you have, should I talk about this? This is where it goes a bit awry. Okay. So there's some very nice things about the curvature as we've defined it. Okay. So if, for example, so one amazing property which proved by Gauss, which he called as theorem egregium, which is literally translates to his amazing theorem. So he was really proud of this one. Is that if you have two surfaces, and say I have some kind of cylinder, let's say, and you have a map between them, such that if you have a map, so you kind of transform one into the other, such that the lengths of any curves on one surface, the images of those curves on this surface, those lengths remain the same, right? And assume this map is smooth. So some say, I think at least second order partial derivatives should exist and be continuous. Then the curvature at every point here is equal to the curvature of the image here, of the surface here. It's an amazing theorem, and it's kind of like a foundational theorem in, it's kind of like a theorem that foundational theorem to do kind of Riemannian geometry. Like it essentially saying you can define curvature intrinsically by just knowing all the lengths on your surface. You don't have to actually refer to any kind of external. So this unit normal is kind of referring to the ambient space external to your surface. You kind of keeping track of that information to compute the curvature. But this is saying that you can so for example, if I have a sheet of paper, and if a sheet of paper can be mapped to a cylinder while preserving distances, right? So if you imagine these grid lines here, right? You can imagine these grid lines go to these grid lines around the cylinder, and these grid lines go to these, right? So, and you can, it's very easy to check. So you locally distances. So if you were to take some small length, some small segment, and so then the distance is just given by, you just do Pythagoras with the grid lines, right? You can do the exact same thing here, right? Because again, like you're just taking, just heuristically, you take very small segments, and you can do Pythagoras with these grid lines. So as long as you can map kind of grid lines to grid lines in such a way that the distance between two grid lines is the same, and the angle between the grid lines stays 90 degrees, this is a map that preserves distances. Okay, this is yeah. And the amazing thing is, so what this is essentially saying then is that the curvature of the sheet of paper, which we all intuitively think should be 0, is the same as the curvature of the cylinder at every point, which is also 0. And we can actually verify this, right? Because okay, it's not okay. Exactly. So, okay, how do you justify that these are the principal directions? So you can think of it as this way: the principal curvature directions can also be thought of as. Remember when I said when you take this derivative of the normal, it may not necessarily lie in the plane that you're considering. It might go outside the plane, so you just take this dot product to only talk about the component inside the plane, right? So these principal curvature directions can also be defined as the directions in which this thing itself lies in the plane. This thing lies in the plane. So essentially, like all the derivatives are in the plane, and you can just think about it as the normal to the curve in the plane, and even the derivative stays in the plane, right? So here you can clearly see that if I have the unit normal coming out this way, and if I kind of vary my point along this, my normal is also kind of moving in the same direction, right? It goes from here to here, and the point also goes like this. So it's kind of moving the same direction as the point. Likewise, this way is just a straight line. The normal direction is not changing at all. So I mean, the derivative is 0. So I mean, this vector is 0. So it's kind of like a degenerate case. But so yeah, these are the two principal directions. In this direction, again, you take the plane, you cut it, you get like a circle here, right? We know circles radius. I mean, circles curvature is 1 over r. We're just talking about plane curvature now. We know this very well, right? So this is the curvature of this circle. And then again, curvature of a straight line, we all agree is 0. So now the product of these curvatures is 0. So kind of that's like a verification. So the curvature at every point stays the same no matter what. So this is like the two perspectives on curvature, which is like how do I say this? In terms of this area scaling and in terms of these product of two principal curvatures, like there's many ways to think about curvature. I gave at least 2 or 3 different ways to think about it there. I gave 1 or 2 different ways to think about it here. We do all this and we show that they're all equivalent to each other. Somehow they end up being equivalent to each other. We just go with the most natural intuitive thing and they just happen to be the same number every time. It's useful to think about stuff this way because, for example, I mean, it lets you solve problems very easily. So for example, okay, here's the problem. Can you take a big sphere of radius capital R and kind of crumble it up in such a way that all the distances are preserved? Okay, so I could imagine I take a sheet of paper. Okay, sure, I'll take one of those. I don't want to ruin my topology quiz paper. Yeah, so okay, this is not a sphere, but you take some kind of surface and you kind of crumple it. I'm crumpling it, but then if I trace any line along the surface, the lengths still stay the same. Like I just need to go, because essentially the paper can be bent, but it cannot be stretched, right? So there's no warping that happens. You kind of just bend all the lines on the surface while keeping the lengths all the same. So you kind of do this kind of thing with the big sphere. And I want to say, can you put it inside a little sphere of radius little r? Right? Is this possible? Can I? So now if I want to state this precisely, I will ask for a distance preserving map that is second differentiable. So that kind of is necessary to discuss curvature at all. Right? So that would be the precise formulation of that problem. So can you do this? Do you think this is possible? So I mean, a priori it looks like maybe it's possible, right? Because again, you do some kind of weird crumpling so that it's like really really wriggly on the surface, like how the brain looks or something, and then you kind of put it inside and somehow it might happen, right? So do you think this is possible? How come? No, but what if? But that's what I'm saying. So what if you get a closed curve? So you take some great circle here, and yes, it's here, but like it's kind of inside. By the way, I'm talking about the region bounded by the circle. I'm not talking about mapping it onto the circle. Yeah, the region bounded by the circle, inside the circle. I'm sorry. Yeah, I should have said that. So if you have the region inside the circle, you could kind of do like a crumbling, and maybe it's jaggedy enough that the lengths remain the same, right? A priori, it's not immediately clear that this map cannot happen. But think about it this way. So I said that my map is distance preserving, right? So I just told you that curvature is also preserved at every single point, right? So say I get some weird surface in here that this can be mapped to in a distance preserving way. I can kind of start shrinking this small circle in such a way such that at some point it just touches this inside surface, right? Why this point exists is the same reason that this has a maxima and minima. This is like a property of compactness for whoever knows what that is. So such a point will exist where, like, if this surface doesn't touch the circle at the sphere at some point already, you can kind of shrink the sphere, and there'll be some point at which it will touch it. There'll be like the first instance of this happening for some smaller radius, right? And so if you were to look at this, so we'll just assume then it's just another smaller sphere. So we'll just assume without loss of generality that it is just touching the sphere somewhere, okay? And so it is just touching the sphere somewhere. And now you look at this, okay? You look at this point where it's just touching the sphere. You look at now you look at the curvature in any direction for this thing, right? In any direction, it's you can like it's the same reason that so if you have one function, if you have two functions that are equal to each other, so if you have two functions f and g, such that so the graphs are like so they both so f of 0 equals g of 0 and f prime of 0 equals g prime of 0 equals 0. Okay, these are also 0. So they kind of both tangent to the x-axis at 0, like the graphs, right? And if I say that f double prime is greater than g double prime, or if one function is greater than the other, then I would then some higher order derivative has to be greater than the other, right? Right. So similar reasoning here. So these two just touch each other here, and they're both they're both tangent to each other here. So in some sense the tangent planes agree, but because so then that means that if you consider some section of them, so essentially you want to consider some direction and a curve in that direction. If you like the best fit circle for the curve on this surface, on the inner surface, has to be smaller, at least at most as big as the best fit circle for the sphere that when you take a plane passing through that point, right? Because it in some sense like the distance of this stays the same, but from the origin, but the distance of this can either stay the same or it has to decrease. It's a similar reason because again curvature is just the second derivative in some sense. Okay, so the second derivative has to be at least as much as that of the bigger sphere. So in particular, all the principal curvature directions, in those directions, those curvatures have to be at least as much as this sphere. So in particular, that product, that Gaussian curvature, which is what this product is called, has to be at least as much as the Gaussian curvature of this sphere. But we know that this sphere has curvature 1 over r square. And you know that this sphere has curvature, 1 over capital R square. And this is strictly greater than this. But then, I meant the best fit circle is smaller, so the curvature is bigger of the inner surface. So that means that whatever you map to, at some point, at all, like at a single point, at least at this point, it has to have curvature bigger than whatever its pre-image was under the map, which is not possible. Yeah. No, it's not like it was inside it, and I've kind of shrunk that sphere so that it's just touching it. Like I'm saying, this is the first point at which, this is the first radius at which any point is just touching it. So in particular, nothing else is outside of the. Yeah, but then whatever new sphere we get has radius at most this much, right? So it's essentially the same problem, right? Because we're just saying big sphere put inside a smaller sphere again. It's right. It's just a different smaller sphere. But if I show it, it's not possible. I mean, so okay. So say this one has radius r prime. I know that r prime is less than r. So in particular, 1 over r square is less than 1 over r prime square. Right. So the curvature is still, inequality still holds. Right. So this is still a smaller number than this. So this is not possible. Well, if it was able to, well, I'm saying that r prime is kind of the smallest sphere inside which it does fit, right? And so I'm saying that it can't fit inside any r prime greater than or equal to r. So okay, maybe this could be equal as well. It can't fit into a sphere for any r prime greater than or equal to r, or less than or equal to r, right? Like whatever this happens to be, it's just some arbitrary radius. Right, so it doesn't matter. So it can't fit in. So the point is that just knowing that distances are preserved somehow gives you that curvature are preserved. There's many ways to prove this, but they're all kind of you kind of have to make these calculations a lot more explicit to do it. So, and I don't think we have enough time for that. So I won't do that. Oh, sorry. Uh, oh, that's much clearer. Okay, yeah. So there are ways to prove this, but yeah, that it's far too much. So, but what I will do is talk about uh, talk about a third perspective on curvature, which and we will definitely, I promise we will prove a nice concrete result at the end of this talk. Okay, I know it's a little hand wavy, but whatever theorems I have stated, we will definitely prove a concrete result at the end of this talk. So let me just introduce. So if you take, let me. Okay, so if I have a sphere and I take a triangle on that sphere. Now I can't just take any three points and draw any curves between them. The sides of this triangle have to be what are called geodesics. So essentially, these are curves, right? So they have a velocity at every point. The point is that and so they also have an acceleration at every point. The point is that this acceleration should always be pointing normal to the surface. So in some sense, the curve is not deviating along the surface. It is only accelerating insofar as it has to hug the surface. Right, so this is like this is one way to define geodesics. Okay, so for example, on a sphere, the geodesics are all just great circles. Okay, so they're all like equators. Because, for example, if you had some, no, actually, I won't get into that. So the geodesics are great circles. So in particular, so you take 3 points, and any 2 points have a unique great circle passing through them. And so you just join them up with great circles. And this is a triangle. Now, okay, so one such great circle is you take one vertex at the North Pole, you take one vertex on the equator, take another vertex on the equator that's subtending, say, a 90-degree angle with the center. Okay? And you take another vertex on the equator. Now these two, so this angle will also be 90 degrees because if you kind of view it from above, these are orthogonal great circles that you're considering, right? One along here, one along here, because their projections are orthogonal. So over here also they have to be orthogonal, right? So and the equator is perpendicular to all the kind of lines of longitude, right? So you get a triangle here, but the sum of the angles is greater than 180 degrees. Each of these angles is 90 degrees. Is everyone okay with this? Does everyone accept this fact? Yeah. So the sum of the angles, summation of the angles is greater than 180 degrees, which is a little weird, but actually it's the same kind of reasoning as the thing I said with it. It's essentially measuring the warping of area, because essentially if you fix the radius of the sphere on a given, so say you take a unit sphere, the area of a geodesic triangle is actually exactly the difference of these two angles. Like it is exactly the excess angle that you have. Like it's equal to sum of the angles minus 180 degrees, I believe. Or maybe up to some constant. I don't recall the exact formula, but it is dependent only on the sum of the angles. Because and so in some sense, the fact that these angles don't add up to 180 is the same reason that areas are kind of warped by curvature. It's kind of this, it's the same thing, really. So this is kind of like an equivalent way of detecting curvature, that the sums of angles of geodesic triangles differing from 180 degrees, right? And oh, by the way, this fact is like there's a really nice proof without words for this fact. Is some simple spherical geometry. So you just complete all these geodesics and those great circles, and those great circles kind of cut the spheres into various sections, and you can just so if you have two great circles, kind of one going like this and the other one going like this, they kind of split the sphere into 4 regions, right? Yeah, exactly. And so essentially the angle between the geodesics is determining their areas. Exactly. So then you can just use the areas to calculate those angles. Use the angles to calculate those areas. And this triangle is just the intersection of 3 of those. So this is kind of why the areas depend only on the angles, right? So this is a measure of curvature. And in fact, this for geodesic triangles, it's really nice. If you take a sequence of geodesic triangles that kind of converge to a point, the curvature of that point will in fact be equal to the limit of this thing. This is a consequence of a theorem called the Gauss-Bonnier theorem. If any of you have heard of it, or this is the local version of that theorem. The global version is something I'm going to address now, actually. So motivated by this, but we're going to do it for a special case where we can do everything formally and geometrically. We don't have to do any fancy calculus. So this is weird, and you can also see that, say, if you have like a saddle surface. Oh, by the way, I never actually gave you an example of. I never actually addressed the sign of curvature. So you can also talk about the sign of curvature. So essentially, if two things are both curving towards the normal, or both directions are curving away from the normal, you can say you pick towards the normal as your positive curvature. Curving away from the normal will assign that negative curvature, and so whatever curvature you get the sign of that will also be the product of these signs. So if both are curving away from the normal, it has positive curvature. But if you have like this kind of saddle shape, sorry, I suppose this goes behind, right? So how would I draw this? Like a Pringles shape, right? Yeah, or on a torus, or on a donut, you get like on the inside of the donut, one way it's curving like this, and the other way it's curving like this, right? So those are negative curvature, and on those you get these triangles are kind of fat triangles on a sphere. There you kind of get thinner triangles. So actually, the sum of the angles then becomes less than 180. So at least in terms of signs, this agrees with curvature. So positive curvature, sum of the angles will exceed 180. Negative curvature, sum of the angles is less than 180. And obviously, when it's flat, you know that this is equal, so zero curvature. So I think this is in fact the formula. For small triangles, this is the area of the triangle even. No, let's not. This is the curvature. Sorry, this is the curvature at a point. If you kind of shrink a small triangle around it and calculate it this way. Anyway, so motivated by this, I want to define curvature on polyhedra. So let's just look at a cube. Right? Now, on a cube, you can draw triangles on one of the faces, but that's boring because that's just like drawing triangles on a plane, right? You're not doing anything here. So this is the sum of the angles here is 180, right? Because it's just a plane. So I should say what geodesics are here. So essentially, when a geodesic stays within a planar face, we're fine. It's just the regular notion of a straight line segment. If you want to go across an edge, essentially you imagine kind of unfolding the net, this into the net of the cube. You draw a straight line there, and then you fold it back, right? So it'll look like this, right? This is what geodesics that go across edges look like on the cube, right? So essentially, Professor Date mentioned in his first talk, he mentioned metrics. So he mentioned coordinate charts and metrics. So essentially, you give this a chart so you take the netting, you put a chart on the netting, and you give it like a regular like flat space metric, and you kind of just fold it back, and you assign the same coordinates and metrics to the faces of the cube. So yeah, so then a straight line here will correspond to the geodesic there under this assignment of the geometry of the cube in some sense. And vertices are weird. Vertices are kind of like singular points. I don't recall if there's a definition of geodesics passing through those. But yeah, so this is what I mean by geodesics. So now I can talk about triangles that lie on more than one face, right? So if I were to talk about a triangle like this, let's say, so these are the three vertices of the triangles. Don't be fooled by these kind of sharp points. Those are just parts of the sides. This sum of angles is still 180 degrees. Why? Because the sum of these three angles is still 180 degrees. Why? Because I can just unfold the netting again. And like I said, I define these geodesics by something that turns into a straight line when you unfold it, right? So then it just becomes a plane triangle. And obviously the angles are still preserved because those are safely in the interior of a face, so nothing happens to them. So the sum of these angles is 180 degrees still, right? So these triangles are flat triangles in some sense. There is no curvature that happens when you go across an edge in some sense, because these triangles remain flat triangles. But, and like I said, triangles within a face are also okay. But if you draw a triangle around a vertex, so for example, this would be, again, so now this is even weirder. So again, these are the vertices. Do not be fooled by these sharp points, right? Again, just a consequence of the geodesic. These angles, again, you get all 90-degree angles, right? So there's some kind of curvature information around this vertex, right? It's a little weird. It's kind of looks like this even, right? And in fact, like I said, this is how we're detecting curvature. So we'll just define the curvature associated with the vertex as the excess angle that a triangle around the vertex has. But in order to do this, we have to show that our choice of triangle doesn't matter. We want this to be an intrinsic property of that vertex, right? I kind of picked a triangle here and prove that. This is fairly easy. By the way, this is for a cube. This holds in general for a polyhedron. So in any polyhedron, I hope it's clear that, yeah, triangles across edges are fine. They're still flat because, again, any two edges, you can at least, the local net, so the net involving just these two faces can be unfolded and it's fine. But oh yeah, another way to see this is if you were to take these three faces and just these three faces and unfold the net, it is impossible to unfold it in a way that kind of in a way that doesn't cause any tears, because essentially whatever these three angles are 90 degrees, and if you want no tears along any of these, then you would end up with a point, and the images of these edges along the unfolding would be something like this. But then these angles add up to 360 degrees, but these add up to 270 degrees. So that's not possible, right? So that's another way to see that this is kind of it's not flat here, it's curved in some sense. It can't be mapped in an angle. So by the way, whenever I say distance preserving, that also implies that angles are preserved, because if say so if I have a point, right? If I have 3 points, 1, 2, 3, and whatever the images, their distances are preserved. So 1, 2, 3, 1 prime, 2 prime, 3 prime, under some distance preserving transformation, then if I have the distance between 1 and 3 is equal to 1 and 3 prime. I mean, it's just congruence of triangles, right? Like the sides are all equal, so the angles also have to be equal. So you can, in general, you do this kind of argument, except you do it kind of locally, where you take a small enough triangle where it's up, so where the space is approximately flat, and then you do this kind of thing. So again, so if any kind of angle issue happens, it can't be a flat thing. Anyways, so we define the curvature around vertices or across edges. So points on the edge have no curvature, points inside faces have no curvature, points at vertices for any polyhedron is defined as the excess angle of some triangle drawn around that vertex. Yeah. Now, how do we? So we want to show that it's independent of our choice of triangle. So I'll make just an illustrative, maybe not green on a green board. So let's say these are some edges that are meeting at some point on our polyhedron, okay? And I draw some triangle across them. So it'll kind of, and then yeah, is everyone fine with this? Right, so this, I've picked 3 points, I'm drawing a triangle around it, right? But now some of these edges, so on some of these faces, I'll just have a regular triangle. Kind of, you consider so when I say triangles, so far I've been meaning geodesic triangles. Now I'm just talking about regular Euclidean triangles. On some of these faces, you'll just get triangles like this, defined by 2 adjacent edges and a geodesic, right? But then on some edges, you'll get quadrilaterals like this, because you'll have 2 geodesics meeting at some vertex and 2 adjacent edges. So these you just split into triangles again, okay? Right? And then you kind of see that so what do we want to prove? We want to prove that the sum of these angles is independent of the choice of the triangle, right? So essentially, you can see that then that yeah. So okay. So if you were to add up all the angles on okay, so you were to add up all these angles, right, between adjacent vertices, that gives 360 degrees, right? Right? And you okay, and you consider the angles of you consider these angles that you get, right? The whenever you have a quadrilateral, the sum of these angles will be what is it, 360 minus this, right? And whenever you have a triangle, the sum of the angles will be 180 minus this, right? So you'll get minus 3 times 180 minus oh, sorry, I'm so sorry. This will not be 360. This will not be 360. Sorry. Let the sum of these angles be something. Be some A. Okay? And the sorry. Yeah. And so you get 3 times, so let's say the 3 angles, so you get angle 1, 2 and 3. And again you take little a, little b, little c. So you'll get that you get A equals, so on this face you want to calculate this angle as 360 minus this plus this plus this, right? So and then likewise here. So essentially instead of 360 minus these, instead of B being equal to 360 degrees minus these two and this, you instead do 180 degrees minus these two plus 180 degrees minus this angle 2, right? I'm just splitting it into two different things. Okay, I mean yeah. So then so I guess these triangles weren't really necessary. So essentially now for every pair of angles like these, you get a factor of 180 minus something, right? Like you get so when I try to calculate this angle in terms of these two, that will be 180 minus these two. This angle will be 180 minus these two plus 180 minus this, and this angle will be 180 minus these two plus 180 minus this. But the thing is that the sum of these angles will also be fixed, because these angles will form complementary angles with this edge, because again flatten, check the angle, will be the same. So each of these will sum to 180, right? But then each of these pairs were adding 180 as well. So you're kind of subtracting, so all the 180s subtract with each other. You get, I'm giving pairs of 180s associated with these angles, the non-vertex angles, right? So all of those cancel out, and you essentially just get, so however many, so you have 3 times 180 minus the sum of the angles, right? Of 1, 2 and 3, because those are the only terms that are remaining. So you get that the sum of the angles. No, I shouldn't say 3 times this then. Sum of 180 minus whatever angle, right? And so you get, so this A is a fixed, it's just based on what the, how many, like what the polyhedron is and which vertex you're picking, right? So essentially then you can solve for the sum of the angles in terms of A. So the choice of triangle doesn't matter, right? And now let's just do a quick. So you're able to now define curvature, right? Of any point on a polyhedron. Now, this kind of analogous thing, this is like a total curvature of some sort, okay? Which is that's calculating how many, like how much total turning is happening. Let's see if total curvature, calculating total curvature on polyhedra gives us something interesting. So if I were to calculate total curvature for a cube, well, every vertex is the same, right? And I showed just now that the sum of the angles You can just pick any triangle, right? Sum of the angles ends up being 3 times 90, 270, right? So the curvature at everything is 90 degrees at every vertex, and you have how many vertices? You have 8 vertices, so 8 times 90 degrees, right? Yeah, and for a tetrahedron, so tetrahedron is a little weird. I should have worked this out beforehand, so sorry. If you pick a vertex on each of the 3 things, you'll get you can just treat it as half of these 2 angles. Does anyone remember the angle for the for a tetrahedron? Should be. Oh, we had a formula earlier for in terms of a, right? So it was just a minus. Sorry. 3 times 180 minus a was the sum of our angles, right? Was our angle sum. So 3 times 180 is anyone? 540. A is just the sum of the angles around these, so that's 3 times 60, right? I'm just taking a tetrahedron, so 3 times 60 degrees, right? And yeah, so the sum of the angles around each thing is 5. Okay. So you're just subtracting one of the 180s off, so this is just 360 degrees, right? And so this is the angle sum, and our curvature is equal to angle sum minus 180 again. So the curvature at around each thing is 180 degrees for a tetrahedron, right? Around each vertex. And how many vertices do we have? 1, 2, 3, 4. I hope I haven't made any mistakes. So 4 times 180 is the same as 8 times 90. Yes. Okay. So 180 times 4 is the total curvature, right? Which is the same as what you had earlier. So that's a bit bizarre. Would you like to try this out on an octahedron? Anyone? Or are we good? Okay. I mean, simple calculation. So it'll be 3 times 180 minus sum of the angles will be now 4 times 60 degrees, right? So 4 times 60 degrees. So 540, 240, 300. Yeah? Just come on. Yeah, 300 degrees. And then there's how many of these? So 300, and then you have to subtract 180. So 120 degrees times how many do you have? So 1, 2, 3, 4, 5, 6. 120 times 6. Is that the same thing as? Yes? Cool. So we get the same thing for even an octahedron, right? So that's a bit strange, and it's not a coincidence at all. This is a consequence of, well, this is the polyhedron version of the Gauss-Bonnet theorem, which is essentially that any 2 surfaces, if they're homeomorphic to each other, so one can be continuously deformed to another. If you calculate the total curvature of both of them, they'll both be equal to the Euler characteristic. So some of you who were here last stems would remember there was a talk on the Euler characteristic given, and there, so I mean, if anyone was there you kind of seen that it was a topological invariant. You'd gotten some interpretations for it. One standard interpretation is just if you have a planar graph, then you take v minus e plus f, right? Vertices minus edges plus faces, or on a polyhedron, same thing, right? So we can prove this. We can prove this quite easily. So what's my statement? My statement is that the total curvature of any polyhedron is equal to v minus e plus f. Okay. How am I going to do this? I'm going to do it via triangles, because I only know triangles, right? So I'm going to do it via triangles. I'm going to consider what's called a triangulation of my polyhedron. Which means that I'm going to cover it with geodesic triangles in such a way that none of the vertices of those geodesic triangles coincide with any of the vertices of the polyhedra. Okay? You'll have to take on faith that you can do this. but you can kind of like, yeah, you can just style your polygon in this way. Yeah. And so you tile it, and now we're gonna do just like a like a count that's one thing in two different ways, standard combinatorial trick. So we're going to count the total number of angles around each of these around each of the vertices of our triangulation. Okay, so the sum of the angles around a given vertex will be equal to the number. So it'll just be 360 degrees, right? So it'll be 360 degrees times number of vertices, right? And the other way of counting all of these angles is that each triangle has 3 of these angles. Now the triangles that aren't so the triangles that aren't don't contain a vertex of the polyhedron in the interior will just contribute 180 degrees. So it'll be 180 times the triangles without the without vertices inside them. So F non-vertex, so NV, and plus the triangles that do have vertices inside them, that just equal to the so this is the curvature, right? So it's just equal to the curvature at that vertex plus 180 degrees. That's this angle sum of the triangles. So so this will be F vertex times kappa plus 180 degrees, right? And so you can just take F vertex times 180 degrees plus F non-vertex times 180 degrees and just combine them into F times 180 degrees. That's the number of faces in this, and you can compute no, have I gone wrong here? And the F non-vertex one, so F non-vertex times kappa so this is just summation kappa. Sorry. This is just summation of kappa at each vertex, right? V, right? So this is the total curvature. This is 180 times, so 180 degrees times F, and 360 degrees times V minus F, right? So this is just 360 degrees times V minus half F, right? And this, for a triangular planar graph, this is the Euler characteristic, because for a triangular planar graph you have that 2 times the number of edges equals 3 times the number of faces, right? So number of edges is just 3 halves times faces. So if you put 3 halves times faces for E in V minus E plus F, this is what you get. So it depends only on this. So the total Euler characteristic of any polyhedron. By the way, when I say polyhedron, it could even be weird, like a weird thing where you kind of you take a donut, and instead of a donut you just take like no, how this look? Okay, and then another thing. Yeah, this kind of thing, right? Where you just take like a blocky donut, and it works even for this. And this has so far we were considering convex polyhedra, so all the vertices have positive curvature. You can get negative curvature triangles on these. You'll get weird negative curvature triangles on these. So this holds even for these, because it just relies on all the curvature following this formula at only the vertices, and the fact that you can do a triangularization. So yeah, and this is just, I mean, and in particular, any planar graph that you put on this will have the same formula, will agree with this number for V minus E plus F. So it only depends on the polyhedron. So yeah. Oh, sorry, I've gone on for way too long. Okay. Yeah, but yeah, that's essentially the Gauss-Bonnet theorem proof for polyhedra. And the thing is, so you guys can kind of also see that this thing is homeomorphic to a sphere, right? So if kind of and so an analogous thing holds on the sphere, because you can just kind of put a sphere on top of this and kind of project outwards onto the sphere, right? That's like a stretching onto the sphere. And so this Euler characteristic is a purely topological notion. Like whatever graph you make on this, you can just project it out onto the sphere, and all the same. It's literally the same graph, right? All the graph theoretic properties hold. So that also has a well-defined Euler characteristic. In fact, it agrees with these. These should have Euler characteristic 2, or is it 1? Anyone know Euler characteristic of a 2, right? Yeah, 2. Right. Of polyhedron is 2. So sphere also has Euler characteristic 2. And in fact, if you integrate 1 over r square over a sphere, so instead of 360, we should say 2 pi here, really. Like, I'm saying curvature is equal to this, but it's only equal to this if you say this in radians. Okay? Like, it's actually equal to this number. Uh, so like 2 pi times integral of 1 over r square over the sphere. You do like you kind of show it for triangles, the Gauss-Bonnet, and then essentially then you take like a triangle around each of the singular points, and you apply the local Gauss-Bonnet to that, and then you kind of argue that you do an integral around this, and that actually is equal to the total curvature inside this, but then that same integral is also equal to the total curvature outside this. And you equate those, and that's what you get. You integrate them back to the Now, in higher dimensions, there are some, it's a sketch of a group as seen involves this Gauss map that I mentioned. The normal vector map that I mentioned, called the Gauss map, the map in the purpose of the sphere. And you essentially you take, so for any point on the sphere, you take the pre-image of this map, and this kind of the pre-image of any given point. Uh, there are n different points. Uh, there's some number of points mapped to it. It's not necessarily an injective map. And essentially, you kind of prove that that the sign, like the points which have positive curvature minus the number of points that are negative curvature is constant no matter what point on the sphere you take. And then you do kind of like you do a similar argument on each of those and follow. I think this only works for division. Sorry, I'm a bit. Yeah. Anything else? But yeah, but the notion of curvature, if you want to generalize curvature, like you have that. So this the version, the way I started things up, this works for like an n minus one dimensional surface and an n dimensional space. So you get one that you can talk about. Right. So it kind of, so if you want to define cross property, these are the elements. So other characteristic is the orthogonal property. You can define that. So you can just take higher dimension of these kind of. We take tetrahedrons. So instead of triangular pieces, we take tetrahedral pieces and triangular pieces. All that. So you can define all characteristics in the same way. Some kind of B minus B plus orthogonal, B minus B plus tetrahedral pieces. And the curvature can be defined in a similar way. So again, you take the derivative of that normal map and the Fourier integral to that. So like those are the elements. How they're connected is the work. Right.
Actually, I'm not sure if this question makes sense, but like the cube, for example, has like a sharp edge at that point, right? So it's sort of not differentiable.
Yeah.
So it's entirely like what you're using is entirely topological property.
In some sense, if you go to you imagine this way. So if you look at the normal unit normal map for this, you kind of think of it as so on the sphere. So these are just like three distinct points on it, right? And there's like a jump that's continuity between them. So it's like one is pointing upward, one is pointing sideways, and one is pointing this way. You can kind of like smooth out this corner and these edges, and that kind of fills in a kind of. So we take a small triangle. That kind of fills in a sort of triangle on the sphere. And then, yeah, so if you were to smoothen this out in any way and carry the total curvature, that will be equal to this. So you can now maybe the limiting process.
I see.
Of smooth curvatures. You can do that.
Thanks.
Yeah.
So we have answer clock at 6:30. All of you should be present there because we'll be distributing the certificate present by the end of the talk. Yeah. We actually don't have copy right now. Okay, this is fine.
Oh, thank you. Thank you. I think the really cool part is you can come up with a natural intuitive definition for curvature in many different ways, and they all are happy. That's not a theory. How do you complicate it? But like it's just like just a mathematical. That. You want to? You can do it. They have it. What you gonna do? The? Just the last. It should have recorded it. This video, but it's the last. You